Hello all, I am Shatadhya Acharya from Vedang Institute of Technology. So in the previous videos, we were discussing about carbocations and carbanions. We have started off with a major classification of organic compounds into two categories. One is acyclic and cyclic, and we went on further classifying them. Then after that, we dealt with how the bond fission occurred in a homolytic or heterolytic manner. What is a homolytic fission? What is a heterolytic fission? From heterolytic fission, we arrived at the conclusion of carbocation and carbanion. What are carbocation and carbanion? Their hybridization, geometry, as well as their stability order. Now in this video, we will be taking up free radicals. Okay, if I consider free radicals, what happens? How are free radicals generated? See, by homolytic fission. By homolytic fission. What do you mean by homolytic? Homo means same. So what we have discussed, if a carbon is bonded to some other carbon or other atoms, for example X, now they both are of equal strength. Okay, the order of strength, or they are of equal power. They are pulling that electron with equal force. Then what happens? Nobody is powerful enough to take away the entire pair of electron. Now the electron pair is distributed equally between both the atoms, right? In between carbon and X. Okay, so what happens? If this is the pair of electrons they are sharing, each atom will move with its own pair of electrons. It will move taking up its own pair of electrons. As a result of which, what will happen? C with an unpaired electron and X moves away with another unpaired electron. Now what will be the charge of this free radical? See, what I have said in the previous video is the charge is only acquired by an atom only when it either gains an electron from some outside atom or it loses its own electron. But what happened here is carbon, it neither lost its own electron, neither gained an electron from outside atom. So here free radical will be a neutral species. Okay. Free radical will be a neutral species. Interesting, right? So here it is a neutral species, but why it is reactive then? Like carbocation and carbanion, it is reactive. Why? See, an atom to be stable, it has to have 8 electrons in its vicinity or in its surrounding or in its outermost shell. Now if I'm seeing this free radical, assuming these all are hydrogen, then here there is sharing of 2 pair of electrons. 2 electrons, here there is sharing of 2 electrons. So I'm getting 3 pairs of electrons shared, that is around the carbon atom there is presence of only 6 electrons plus 1 unpaired electron, 7. Okay. So total number of electrons around the carbon atom is 7. It is still deficient, right? It needs one more, or it needs to acquire one more electron in order to be stable. That's why this need makes that particular carbon or that particular free radical reactive. Now see, carbocations were formed after the carbon atom lost electrons, right? The carbocation was deficient in electron. This free radical is also deficient of electron. So most of the reactions shown by, or the stability order, or whatever we compare, most of the reactions or similarities are shown to carbocation. Free radical is showing most of its similarity to carbocation because both carbocation as well as free radicals are deficient of electrons. Okay. So if I compare the stability order, then it follows the same: 3 degree, greater than 2 degree, greater than 1 degree. Just like our carbocation, because both are electron deficient species. Okay. Now if I see the hybridization, here what happened initially, obviously it was an sp3 hybridization. Here, while coming to the free radical stage, did it lose both of its electrons? Obviously no. It is still having one more electron. So I will count this orbital also in considering its hybridization. So 3 orbitals are already used, plus the 4th orbital also contains 1 unpaired electrons. So here what concept we gained is while calculating or while finding out the hybridization, we will include sigma bond, pi bond as well as unpaired electrons. Okay, we will include sigma bond, pi bond and unpaired electrons also. So here what happened? Hybridization is still sp3. Okay, and the shape is tetrahedral. Okay, so this was all about free radical. Now moving on, we will see something more in detail about attacking reagents. Okay, this was all about our substrate. Our substrate undergoes the bond fission. Now the bond fission can be homolytic or heterolytic. If heterolytic, we are getting the concept of carbocation and carbanion. If it is homolytic, then we got our free radical. We understood the hybridization and shape of free radical, the stability order for free radical. Now we will understand something more about attacking reagents. Okay. So fission of covalent bond is done. We will see about reagents. Now reagents are attacking species, those atoms or ions which attack our substrate. Okay, so basically understand a situation. This is exactly like the human nature. Okay, suppose I am seeing two people are having some difference of opinion. Okay, they are not in good terms among each other. So me being the third party, it will be easier for me to break them apart, to rift them apart, right? Because they are already having a difference of opinion. Okay, they are already not in good terms with each other. So basically, if the reagent comes and the reagent is seeing that a molecule is polar, right? That means it is having charge separation, difference of opinion. Then what it basically does? It attacks the site where there is difference. Okay, it attacks that site of the particular compound or the organic compound where there is certain difference of, not opinion in case of organic compounds. Here we are taking up charges. So where there is difference of charges, where there is a creation of dipole, that is the site of attack for our organic reagents. Okay, so organic reagents are the attacking species. What they do? They attack our organic molecule at the site where there is difference of opinion, where there is difference of charges, which we call, in the language of chemistry, we call dipole moment, or dipole. Wherever there is creation of a dipole, the organic reagent finds it easy to attack at that particular site. So in that case, dipole means there will be two poles. One will be positive pole, one will be negative pole. So the attacking reagent can go for attacking both the poles, either positive pole or negative pole. To what pole it will attack, to what site or what charge it will attack, depends on the charge of the reagent itself. If the reagent, and we know opposites attract, if the reagent is negative, then it will obviously hunt for a positive site of attack. If the reagent is positive, then it will hunt for a negative site of attack, right? If both the persons are not in good terms with each other, then I will basically try instigating the person with whom I am having my selfish needs, right? So basically, the reagent will go and attack that particular site depending upon its own needs, own charge. If it is having negative charge, it is having a lot of negativity around itself. In order to pacify it, it needs such kind of atom which is having deficiency, and it can just vent out, or it can let out all its negative charge on that particular atom and neutralize itself. So positive will hunt on and go on for attacking a negative site. Now if a positive atom is coming, it is in deficiency or in need, so it will search for a site which is having excess of negative charge. So it will go for attacking a negative site. So based on the charge of the reagent, we classify reagent into two basic categories. Okay, depending upon the charge of the reagent itself. Now, if the reagent is positive charge, that means it is having a lot of electrons, it will be hunting for a positive site. Positive, if I am considering atom, then nucleus is considered as a positive center. So the negatively charged ions or the negatively charged reagents will have a special affinity or a love for a positive site. That means a nucleophilic site. Means we got a new word here, which is nucleophilic. Nucleophilic site. That means that particular site which is having a deficiency of or nucleophile. First let us understand what is the reagent is called the nucleophile. What do you mean by nucleophile? Nucleus loving. So what I was saying, if the reagent is negatively charged, it will go on hunting for a positive site, and positive is the nucleus. So it will have a love for nucleus. That's why its name nucleophile. Phile means affinity or love. If the atom in itself is negative, then only it will go on hunting for positive site. So if that atom is negative, it will be called a nucleophile. That means that particular atom which has a special love for a nucleophilic center or a positive center. Okay. Next, if I say, if the atom is in positive in itself, it is having deficiency. So it will hunt for a site which can make up for its loss, right? Which can make up for its deficiency. If it is having lack of electrons, then it will obviously go on hunting for a site where it can get some electron density sources or a negative like ion source. That will be, negative ions are called as electrons. So that particular atom which is positive in itself and it will go on hunting for a positive site, sorry, a negative site, that particular atom is called a electrophile. Electrophile means electron loving. Electron loving species are called as electrophile. Okay, and nucleus loving center atoms are called as nucleophile. Okay, those atoms which are in itself negatively charged, they will hunt for a positive center and they will come under the category of nucleophile. If those kind of atom, those who are negative charged, they will hunt for a positive center, they are called as nucleophile. If the atom is positively charged, it will hunt for a negative center, they will be called as electrophile. So nucleophile is designated as Nu minus. That means that particular atom which is in itself negatively charged, and electrophile is designated as E positive. Okay. Now, what kind of atoms comes under the category of electrophile and nucleophile? Obviously, electron, suppose I am saying nucleophile, means they themselves are negatively charged, then they can have that negative charge in the form of a negative charge only, first case, and second thing is in the form of lone pair. So the atoms, the anions and the atoms consisting of lone pair of electrons fall under the category of nucleophile. Those atoms, or I can say anions and neutral atoms, having lone pairs. Okay, so anions and neutral atoms having lone pair of electrons, they fall under the category of nucleophile. Okay, and if I say electrophile, then cations and those atoms which are connected to or which are bonded to a highly electronegative atom. Suppose for example, if I am saying, let us write the definition first or the example first. Cations and those neutral atom that are bonded to a more electronegative atom. Okay, so for example, let us see, if I am giving you the example of C double bond O, suppose carbon is bonded to oxygen. Now here oxygen is highly electronegative. In our periodic table we have three very highly electronegative elements which we call FON, F-O-N. Fluorine, oxygen and nitrogen. They are very highly electronegative elements. So if carbon is bonded to oxygen, then oxygen being more electronegative has a tendency to attract the shared pair of electrons towards itself. That means if this is the shared pair of electrons, then oxygen will be attracting all the electron density towards itself. Therefore, oxygen will acquire a negative charge and carbon will acquire a positive charge. Okay, but the bond is not entirely shifted upon oxygen or carbon. Therefore, there will be development of partial charges. So we show it as delta negative and delta positive. Delta means partial development of charges. And why this arises? This is due to electronegativity difference. So when there will be partial charge separation in between them, there will be some kind of polarity. Then this carbon site that is electron deficient, the carbon site has become electron deficient. Now this is the appropriate site of attack for a nucleophile. Okay, it is in itself a positively charged atom. So a negatively charged atom can easily attack this site. So carbon positive site is a site of attack for a, I guess I have written it wrong. Yeah, electrophiles are those. Okay, so carbon has a positive charge on itself. Therefore, carbon is the site of attack for an electrophile. So I can say carbon is having a electrophilic center to which a nucleophile comes and attacks. Nucleophile is a negative charge species. It will come and attack to a electrophilic center. Electrophilic means electron deficient center. Okay. So the example of nucleophiles are anions and neutral atoms having lone pairs, and electrophiles are cations and those neutral atoms that are bonded to a more electronegative atom. Now for this, let us see some examples so that you will be clear on electrophile and nucleophile. Suppose I am giving you these examples, you have to classify them as electrophiles or nucleophiles. Okay, pretty simple. The first one, if I see, it is HS minus. Clearly it shows the presence of negative charge on sulfur, therefore it behaves as a nucleophile. Now if I see BF3 here, it is a neutral molecule, but boron atom is bonded to 3 fluorine atoms. Therefore there are 6 electrons around boron. Therefore it is an electron deficient atom. Okay, it is in itself a positive atom. Okay, it is electron deficient atom, so it will behave as a electrophile. Now if I see C2H5O minus, negative charge, obviously nucleophile. If I see CH3, here nitrogen is having a lone pair of electrons, therefore it will behave as a nucleophile. Now if I see Cl plus, positive charge, electrophile. If I see CH3CO, again this is the example which I have given you. Here carbon will have a positive charge because oxygen being more electronegative, carbon will have a delta positive charge because oxygen being more electronegative pulls out or takes away all the electron density, most of the electron density towards itself. Therefore carbon will develop a partial positive charge on itself, and that is therefore making it a electrophile or electrophilic center. Okay, NO2 plus, electrophile again. So I guess after solving these, you are clear about what are electrophiles, what are nucleophiles. And before moving on to the other lectures, you have to be very sure about electrophiles and nucleophiles, because these are something which we'll be using in our entire organic chemistry. Organic chemistry is incomplete without the understanding or the knowledge of electrophile and nucleophile. Okay, so now let us see. We had seen substrate and reagent. Next is electron movement in organic reactions. Now, we have seen homolytic bond breaking, heterolytic bond breaking. So what was happening basically? Electron was shifting from one atom to another. So how you will denote them, like from if electron is shifting from one atom to another, how we will symbolically denote them, right? So let us see. If I'm taking the example carbon X. Now we will assume X is a stronger friend of carbon. X will take up all the electrons along with itself and leave behind a positive charge on carbon. Okay, so in that case I will show the arrow like this, which means the arrow will start from the atom which is giving its electron and will end at that atom to which the electron is shifting. So if I have to show that X is taking away electron, I don't need to write a long paragraph on it. Simply I can symbolically draw this, and this arrow will mean the electrons which are being shared between carbon and oxygen is now shifted entirely on the heteroatom X. So this will mean carbon positive, of course 3 bonds are there, plus X negative. Okay. If I have to show X is stronger than, carbon is stronger than X, then here the electron pair will shift from X towards carbon. So now the bond will be shown like, or the arrow will be shown like this. Simply seeing the arrow, you can conclude that electron pairs are shifted to carbon and X is moving empty-handed, right? Now, if I have to show homolytic cleavage, that is, the bond is breaking equally, homolytically, then how I will show? Suppose carbon-carbon, this bond is there. If I have to show homolytic bond cleavage, that means the arrow will be half-headed fish hook arrow. This means the electron pairs, only one particular electron pair is moving to one atom and the other electron pair is moving to the other atom. So this means we have a carbon free radical or two carbon free radical. Okay. And if I have to suppose there is an atom Y, it is the doubly bonded here and here it is singly bonded. Suppose for example, I have to show that the pi bond is shifting from the other bonded carbon, like it is being bonded to one particular carbon and here it is bonded to another carbon, C1 and this is C2. So if I have to show that the pi bond is shifting from C1 to C2, then how I will show? The arrow will move from the side from where the electron is coming, and the arrow will lead to the place to which the electrons are getting transferred. Okay. If I have to show there is a lone pair of electrons on Y and it has to pass through this carbon or this bond, then it will mean like this. Okay. So I hope in this video you are clear about how the movement of arrow is done, what are free radicals, what are reagents, the types of reagents, and with specific examples we have seen what are electrophiles and nucleophiles. In the next lectures, we will be seeing the factors which are responsible for stability of organic compounds, and that is going to be a very important lecture. We will be taking up various factors like inductive effect, resonance effect, mesomeric effect, and those are like these will be carried forward in like wherever you go and whatever organic chemistry you study. These are very important concepts. So before watching those, I hope you are clear about this, and if not, then regularly like read some books or repetitively see those videos unless and until you are clear. Otherwise, the upcoming lectures will be a burden for you. So that's all for that. Thank you for watching. Thank you so much.